Hello everyone, my name is Esteban Padilla and this is my presentation for the Learning Robots project, which I called Easy Object Conscious SLAM. The purpose of OCSLAM is to allow the robot to understand not only where it is and where it's going within an environment, but also to have semantic information about the entities in this world. This will allow the robot to more properly interact with its environment. This project proposes a solution that allows the robot to have a consciousness of where their objects are and what classification they have. Here we have an overview of the architecture of the system. We first have a robot with three sensors: the camera, the lidar, and the encoders in the wheels. The camera outputs an image that is read by a YOLO network that outputs a series of bounding boxes corresponding to the objects found within the image. The lidar outputs a series of readings that can be used by the SLAM toolbox to generate the map. And finally, the wheel encoders can be used by the robot to perform odometry and understand where it is in the world, and also to perform a PID control system to control the direction and velocity of the robot. Finally, the consciousness node understands the bounding boxes, the lidar system, and the robot pose to output a series of object classifications with their position in the world. For this project, we will be using the TotalBot 3 robot, which has exactly those three sensors, and we will be running it in a simulated world in the Weebot's environment. To connect the ROS nodes to the Weebot simulation, I created a wrapper using the Weebot's ROS2 driver that allows me to read the position of the encoders and set velocity information to the wheels. Since the robot does not have an IMU, we rely entirely on the readings of the encoders to perform odometry. I am using the classical odometry equations that take into account the difference in the position of the right and left encoders, the radius of the wheel, the distance between the wheels, and the time step to update the heading at the X and the Y positions. We can also use an inverse of these equations to receive a velocity command with a linear and angular velocity components and transform it into the angular velocity of each of the wheels. With these equations, we can receive a velocity command, transform it into angular velocities, and send it to the simulation, and also receive the information from the encoder and use it to perform odometry of the robot. We can then send this odometry through a topic. For SLAM, I will be using the already created SLAM toolbox, which consumes the topic created before of the odometry and creates a map like the one in the image. The SLAM toolbox can also occasionally correct the estimation of the position by using feature tracking. Now that the robot knows where it is, we can begin teaching it what other objects are there in the world with it. Here we have an implementation of the YOLO network, and as you can see, it reads the information from the camera and creates bounding boxes around a series of classified objects. To train the model, I took around 800 photos from the perspective of the robot from the objects from different angles. I then manually created the bounding boxes around each one of the images. I then used transfer learning to take a model that had already been pre-trained with millions of images and help it learn from my images using my classes. Through a series of experiments, I found the best combination of parameters and found that the nano model with 64 batches of training, image width of 224 pixels, and around 237 epochs outputted the best precision, which was close to 90%, with a speed of 625 FPS. Now that we have the YOLO information, we can begin processing the lidar. The lidar outputs a series of distance readings separated by an angle increment in a circular pattern. To get the X and Y positions of each one of the points, we can use the following equations. We now have the YOLO bounding boxes, the lidar points, and the position of the robot. And we can use this information to extract the position of the objects and classify them by using projections. To project the YOLO bounding box from a 2D plane in the image into a 3D area in the environment, we could use a projection matrix like the one right here. The projection matrix takes the intrinsic values of the camera and the rotation and translation matrices of the robot to project a point in an image into the 3D world. The intrinsic parameters of the camera are defined experimentally with calibration. With this projection matrix, we can project each one of the pixels in the camera into the 3D world like we see right here. And if we continue the points into infinity, we can also understand where they intersect in a plane. We can use this information to know where the points of the YOLO box intersect with the plane of the lidar. By combining the projection matrices with the boxes of the YOLO network, we can create 3D bounding areas that are projected into the 3D world. By combining these projections with the lidar information, we can now correlate each one of the points in the lidar to each one of the boxes in the image, like this. However, before we can start using these projections, we need to calibrate the camera to extract the intrinsic parameters mentioned before. For this, we can use CV2's calibration function that takes a checkered pattern and a series of images to calibrate and extract the intrinsic parameters. Also, a checkered floor is used to test if the calibration is correct. Here we can see that although it is not perfect, the error is minimal. Now, to extract the position of the objects, we cannot simply use clustering to extract all the islands found in the points. As you can see here, only one of these islands corresponds to the flowers, and the others correspond to the wall behind it. So we need to take into account several edge cases. The first one is this one, when an object is in front of a background, and the background is also considered part of the bounding box. The second edge case is when the projection of one object that is in front overlaps with the projection of another object that is behind. Here in this case, for example, the dog, although we have a series of points right here that correspond to the dog, the series of points right here will correspond both to the dog and to the ball. A similar thing happens when an object is detected both by the camera and by the lidar, but its bounding box overlaps with that of an object that is too far away to be detected by the lidar. In this case, for example, these points right here would be identified both as a ball and as a shelf. To counteract these edge cases and create an appropriate algorithm, I start with a series of assumptions. First, each bounding projection contains one and only one correct object. This is because, of course, the YOLO network outputs a single bounding box for each object. Since the actual object lies at the center of its YOLO box, the correct island will be the one closest to the center line, also called the bisector, of the projection box. Because we're dealing with a flat surface, closer objects will cast a projection that is closer to the camera regardless of the size. Two objects cannot lie in similar coordinates in a way that makes them overlap, and if a new object is detected that is close to an old object of the same class, it is considered the same object. With these assumptions in mind, we can create the consciousness algorithm. First, we assign each one of the points to each one of the bounding boxes, and do point clustering to extract islands. Here we have one island, two islands, and three islands. To choose the correct island, we can use the assumption that the correct island will be the one closest to the bisector of the projection. In this case, this one right here. Then we can use the translation and rotation matrices of the robot to correspond this object island into the 3D world. As mentioned before, it can occur in certain cases when two objects are detected in the same position, so conflict resolution needs to be applied. The first step to solving this collision, as mentioned before, is to check which one is closest to the center line. In this case, for example, this cluster is closer to the center line of dog, and this cluster is closer to the center line of ball. So in this case, we can classify them correctly. The second step is to check if there is a conflict between two different projections. Take into account the projection that is closest to the camera, like this one right here. In this case, the ball is closer than the shelf, so this cluster will be detected as a ball. And of course, if the objects do not overlap in any way, there is no conflict and nothing needs to be done, we can keep both objects. Finally, if a new object is found in the same position as an old object of the same class, we can consider that it is the same object and maybe it has moved a little bit, or there is a small error in the odometry. In this case, we can merge both objects by doing a moving average of the position of the objects and taking the largest size. Now, this algorithm is good, but it is not perfect. Sometimes, due to imperfections in the YOLO network or random points in the lidar, ghost objects can appear that are only there for a few frames. If we keep all of these objects, in the end, it is littered with objects that should not be there, like the one in the image here. So to move away from that, I move from hard decision into soft decision. This means that instead of an object being absolutely there or absolutely not there, it has a confidence or a probability that it might be there. Here we can see, for example, that the ball in the front has a 90% of probability of being there, while the ball in the back has a 20% probability of being there. This could mean that the ball in the back is actually not there. To begin soft decision, I assign a presence confidence that is equal to the confidence of the YOLO network divided by a constant f. This constant is the amount of frames that I consider to be necessary for an object to actually be there. In the case of this project, f is 5. Then on each subsequent iteration, we consider the previous presence confidence and the new YOLO confidence multiplied by a value that gets closer and closer to 1 as the frames approach the number of frames necessary for presence. Although soft decision makes the system almost perfect, there are still two edge cases that are not solved by this project. The first case is when an object has legs. In the case, for example, of tables and dogs, the legs of the object are too far apart to be considered part of the same object. The second edge case is the corner problem. As we can see here, if the corner of an object that is not classified, like a chair or a wall, falls within the bounding area of an object that is too far away for the lidar to detect it, an incorrect island will be detected and an incorrect object will be added to the list. If this object is present for enough frames, it will remain forever and there is no way to solve this that I can see. Taking these limitations into account, we can see the results of the project. Here we can see that the robot is correctly doing the localization and mapping of the robot while simultaneously detecting and classifying the objects correctly within the 3D world. Here we can see a person, a table, a shelf, a wall, and here we can see, for example, the corner problem being present. The dog is here with its two legs as different objects, and the extinguisher is also there. The gnome is detected correctly, And finally, the 2 doors and the flowers will also be detected. Now, by applying subdecision, as I mentioned, we can make sure that the system is correct. If we lower the threshold of the subdecision, for example, this time to 0, we can see that a series of ghost objects start to appear. Here we can see a gnome, for example, with only 16% of probability, or another gnome with 40-something% of probability, etc., etc. If we crank this subdecision threshold again to 80%, these objects disappear, and only very confident objects remain. Finally, the tracking system has the side effect that if an object is moving slowly and the robot is observing it while it moves, the map will be updated accordingly and the object will be tracked across time and space. With this simulation and a presence confidence threshold of 80%, we can see that all 10 objects were detected correctly, with 3 additional objects due to the legs of the dog and the table, and 2 additional objects due to the corner problem. If we consider the legs not to be a problem, the precision of the system is 81%. If we consider the legs to be incorrect, we can say that the precision of the system is 62%. And if I were to fix the corner problem, I would reach a precision of 93%. And the sensitivity, of course, is 100% because all true objects were detected correctly. And that would be all. Thank you very much for your attention.